now we're looking at different examples of data types that you could get and how to go through all those steps, but more, just as important, how you decide on which test to do. Okay, so we're looking at this set of data right here, and what I said in the video was that the way you decide which test to do is you look at your data, and if you've got two variables and the variables happen to be of the same type, so we've got shell length versus shell length, and we want to see if there's a difference between the shell length of this population and the shell length of another population. In that case, the test to do is a t-test. Okay, so we've looked at the data, we've decided which test we want to do, and now we'll proceed to do the test. And remember, in my video, I said that in my previous video, in the overview, I said that there were essentially 4 steps. First one is that we make a null hypothesis. The second is that we calculate the test statistic. The third is that we determine our degrees of freedom and thereby find our critical value to compare our test statistic to, and based on the comparison of the test statistic to the critical value, we make our conclusion about whether there is a significant result from our test, or whether there is no significance there's no significant difference in the data, and we have to accept the null hypothesis. Okay, so let us begin. Just a little bit of introduction to the t-test and and what it's there to do. I think that will explain the steps that we have to go through. Now, the t-test, in terms of the number of steps needed to do the t-test, I think has the most. And I don't think that in any A-level exam you'll be asked to do the entire t-test, but you don't know which aspect or which part of the t-test you will be doing. So I always tell my students that, be prepared, be able to do all parts of a t-test, and then when you are asked to do any one of those parts, it should be relatively easy for you to do. Okay, now t-test is essentially a comparison of 2 normally distributed populations to see if there's a difference in those populations. So here we have our variable, which is x. Okay, no. So here we have our variable, which is the frequency. Okay, so it's the number of organisms. And here we have the variable that we are measuring. In this case, it would be shell length. Okay, and population 1 has a few individuals that have got a very short shell length. It's got more individuals that have got the average or around the average shell length, and it's got a very few number of individuals that have the very highest shell length, and that is essentially what we call a normally distributed population. So that is that's our population 1. That is, or let's call that our population A. And what we want to see is there's a different population. So maybe the population that we drew out was our first one there. Now, if we were on the same graph to draw the next population, our statistical test is there to show whether is the next population, and I'll just change the color here, is our second population very similar to the first population, or is it different? Okay, and the way we do that is by kind of using essentially 2 parameters that characterize that population. So if you have a normally distributed population, one of the things that characterizes what that population or the type of that population is the average, the mean. The other thing that characterizes a population is how spread out so your mean might be the same, but the data might be more spread out. So the other thing that characterizes the population is the spread. Is the spread of the data, and the spread of the data is usually given by the variance of a population, and that's kind of related to, well, it's not exactly the same, but it's highly related to the standard deviation. So I hope, in basic terms, the average is telling us something about that population, and that's essentially where it is on this x-axis. But the variance is also telling us about that population because it's telling us how spread that population is. And both the variance and the average have a part to play in calculating our test statistic. And remember, this is essentially what it's all about. We're comparing these two populations to see what the difference is between them. If the difference between the two populations are large, then we're going to get a big, relatively big t-value. But if our populations are very close together, then we are going to get a small t-value. If we get a big t-value, there's a higher chance that it's going to be bigger than the critical value, and therefore we are going to see a significant difference, and that would make sense. And if our t-value is small because the populations overlap a lot, then there's a high chance that our t-value is not going to be big enough to be bigger than the critical value, and therefore we're going to get a difference that is not significant. Okay, so that's essentially what we are doing. And now let's kind of clean all this up and start looking at the calculations. The first thing that let's just have a look at the equation for t, because that's going to explain the steps that we'll have to go through. And I haven't memorized this, I'm going to have to copy it. But the t value is calculated by the following. T equals, and there might be some variations on this, essentially the difference between the mean of the first population and the mean of the second population. And these two lines on the outside mean ignore any negative signs that come up here. So we just want the positive value of the difference between the means. We're not really concerned with the negative part of it. Okay, and that we are going to divide by the variance of the first population divided by the number of items in that population, plus the variance of the second population divided by the number of items in the second population. Okay, so add those two together and square root that, and then once we divide the difference between the mean by that value, we should get t. Okay, so the first step in doing the t-test is going to be to determine the average of each population, and for each population the variance. Okay, now remember, it's highly unlikely that you'll have to do all parts of these steps, so don't be daunted, but you do have to understand every part of the steps because you don't know what you'll be asked to do. So I'm going to clean this up and then we'll start with our data. Okay, so there's a few kind of terminology things that we should get out of the way first. Each of these values, so we've decided that our first population is going to be x1 and the second population is going to be x2, that's fine. Each individual value, so 46, 50, 45, those are simply x's. They're all individual x's. The average of all these values is given the symbol of x bar. Okay, so x bar 1 will be the average of 46, 50, so 46 plus 50 plus 45 plus 45 plus 63 plus 57 plus 65 plus 73 plus 55 plus 79 plus 62 plus 59 plus 71 plus 68, all divided by the number of values that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, divided by 15. So x1 is 68 plus 77 equals, divided by 15 equals 61. Okay, so that is the average. So 61 is x bar 1. That's the mean of the first population. X bar 2 is going to be 23 added to, so it's going to be the average of all these, equals 33. Okay, so x bar 2, according to my calculations, equals 33. So we've got our average of each of these two populations. That is step 1. Okay. Now, the other thing that we needed to calculate in order to get to the test statistic t was the variance. So I'm just going to bring up the equation to calculate the variance. Okay, and I'll just tidy all this up first. So oops, I forgot my number. Undo. 61 and 33. Terrible, Dr. Bhavsar. 61 and 33. Okay, so x bar 1 equals 61, x bar 2 equals 33. Okay, so the next thing is the variance, and the variance is given by s squared equals the sum of all the x's squared, or the sum of all the x squareds, minus the sum of all the x's squared divided by n, and all of that divided by n minus 1. Remembering that for each population, n is going to be the number of items in that population. So let's get on with that. Okay, so the way I would do this is I would add columns. I would add columns to my original data to help me with all the individuals. So I would always advise you guys, any multi-step calculations, put as much down on paper as possible. Okay, there seems to be a trend nowadays of doing as much on the calculator or doing as much in your head at once as possible. You don't have to prove anything to anybody, just get it right. Okay, so let's begin. So we've got our x's here. Essentially, these are all the x's. And so one of the things that they want, or we need, is, let's just move this out of the way. So x bar 1, 61. Okay, so one of the things that we need to do is square the x's. So all the x's, so the first thing we want is this, essentially. And so to get that, we're going to have to square each x in turn. So 46 squared is 2116. 50 squared 2500. 45 squared, 45 squared, 2025. Well, let's get back together when I've done all the x squareds. Okay, welcome back. What I've done then is I have squared each of these values. 46 squared, which has given me 2116. 50 squared, that's given me 2500. 45 squared, that's given me 2025. So those are all the individual x squareds. But remember, we have to sum them. So we have to get all the individual x squareds and then add them together. So added together, I get 57623 right here. And this is equivalent to the sum of the x squared, that is that part. The next thing we have to do is get the sum of all the x's and then square that. So the sum of all the x's, so adding up all the x values, 46 plus 50 plus 45, and so on down here, that gives 915, and that is essentially the number that would be in this bracket right here, 915, right here. Okay, so let's do the parallel. Let's start putting these numbers in. So the variance is going to be equal to the sum of x squared, which is going to be 57,623, minus the sum of x, which is 915, but we have to square that, and then that's going to be divided by n, and in this case n is 15 because there's 15 values, and that is going to be divided by n minus 1, so 15 minus 1, that's going to be 14. Okay, so again, I write down the numbers into the equation. I do everything step by step. I don't rely on kind of putting everything together right at the end. Okay. Okay, so next, kind of let's flesh these numbers out. So 915, so that's the, need to get a value for that. So 915 squared divided by 15 is 55,000. So that's 57,623 minus 55,815 divided by 14. This is equal to 57,623 minus 55,815 equals 1808. Divide 14, and my variance is 12914. And it carries on, but I'll work with this. Okay, so my variance for the first population, so the variance of my first population is this, and the average for that first population was 61. Okay, so I've got my two parameters that I'm going to need to calculate t in the equation later. All right, so I've got my average and I've got my variance. Now I'll join you again when I've calculated the average for the second population and the variance for the second population in the same way. Okay, so we are back now, and at this point I have now got the I've just worked out the variance for the second population. That is 50.57. So what does this mean? What it means is that the first population has an average of 61 and it's got a variance of 129.14. On its own, that doesn't tell us much. However, the second population has an average of 33, so significantly lower, and it's got a smaller variance of 50.57. So if we were drawing the graphs of these, the first population would have a high average and a large spread, whereas the second population would have a spread which would have a lower average, okay, but it would have a smaller spread of the data. And what the t-test then uses is these values to compare whether these populations have a significant amount of overlap or not. And if they don't overlap significantly, then our t-value is going to be large, okay? But if they do overlap significantly, then the t-value is going to be small, okay? And that is what the t-test is trying to get to, is that are these populations essentially the same, in which case there'll be a large overlap and the difference between the two populations is going to be small. But if there's not a large overlap between the two populations, then the difference between the two populations is going to be big, and therefore the t-value is going to be big. So that is what we're going to look at next. So essentially we plug these values into the equation to work out t. If the difference is big, then we get a big t-value. If the differences between the two populations are small, then we'll get a small t-value. And remember, on its own, the t-value doesn't say anything until we compare it to the critical value, and we'll also go through that process. Okay, so we meet again now. At this point, what we've done, I've just listed the key values that we'll need to in order to calculate t here, and just put the equation here. Let's start doing that. It occurs to me, however, there's one thing that I kind of missed saying, which is just this idea that the spread of the population can be measured using the variance. Sometimes, so the variance is given the symbol of s squared. That's the variance. So the s squared is the variance. That's what we calculated before. Okay. However, another measure that's sometimes used is the standard deviation, which is simply s, and it's basically the square root of whatever your variance was. Okay, so just in case in an exam question you're given the standard deviation, don't get all confused. Just remember that essentially what they've given you is s, and in order to get to the point where you can use the variance, you simply have to square that value. Okay, so now let's get on with it. So essentially you're just kind of replacing all our symbols now with numbers. So the mean of the first population was 61 minus 33. Remember, at this point you could get a negative value. Maybe it could have been that our second population had a higher average. That's fine, because the modulus sign means that whatever number you get, you take the positive value, even if you had got a negative value at this point. Okay, so that's divided by the square root of the variance of the first population, which was 129.14, divided by the number of values in population 1, which was 15, plus the variance of the second population, which was 50.57, divided by, we had the same number of values in the second population as well, 15, and that calculation time, again, I wouldn't just plug in all the numbers and get my t-value, I'd do it step by step. So I'd do 61 minus 33, so I'd have 28 divided by the square root of 129.14 divided by 15, 8.61, plus, then I'll do the other one, 50.57 divided by 15 equals 3.37, Okay, so I'm not losing track of what I'm doing. And then I would work out the square root. So step by step, guys, step by step. 8.61 plus 3.37, okay, 11.98. So I want the square root of 11.98, and then that is equal to square root that 28 divided by 3.46, and that should give me roughly 8.09. okay, so you might get a slightly different number based on this, or you can tell me if I've gone wrong, horribly wrong somewhere in my calculation. Okay, but yeah, we've got t is equal to 8.09. And what does that mean? At this point it means absolutely nothing. So what we've done is, oh, actually, you know what I didn't do? I didn't make a null hypothesis. Okay, so let's just do that. Okay, so before we started, what we should have done is make a null hypothesis. So our null hypothesis should have been, there is no difference between the two populations of mussels on the seashore. Okay, now in a regular question you would get some variable that might be causing the difference. So maybe they were looking at the shell lengths of mussels near the seashore versus the shell lengths of mussels far away from the seashore, and therefore the distance from the water level might have been the factor that's affecting the mussel lengths or mussel shell lengths. So that would have been something that you would have included in your null hypothesis, that perhaps the distance from the seashore doesn't affect the shell length. Okay, so that would have been the null hypothesis. So we got our null hypothesis, so that was stage 1. Now we've just done our stage 2, which is we've calculated the t-value based on our data. So that's stage 2 complete. And now stage 3 is going to be to work out the degrees of freedom so that we can get our critical value. Okay, now remember that for a t-test, the degrees of freedom is given by the number of values in your first population plus the number of values in your second population minus 2. So in this case that is equal to 15. So d degrees of freedom equals that. So the degrees of freedom in this case is equal to 15 plus 15 minus 2 is equal to 28. So we've got 28 degrees of freedom. So we're next going to look at our critical value tables. I'm going to look at our critical value tables, and remember, if you've watched the first video, you should remember that when we get our critical value table, we're going to look across 5 to 5% level of significance, and we're going to look down the table for our degrees of freedom of 28 in this case, and wherever these two meet, that is going to be the critical value for our test. Okay, so let's proceed. Alright guys, and we are back, and now we have our critical value table. Okay, now these tables are different for each of the tests. We have a table of critical values for a t-test here. Okay, and we have worked out, so remember our t-value is 8.09 that we've calculated, and the degrees of freedom we have is 28. So standard, unless otherwise stated, what you're looking for going across is the significance level of 5%, which is equivalent to a probability of 0.05 being wrong. Okay, and you're looking down now here, you're looking down for 28. So we look down and we find 28 right here. And so the point at which these two meet is 2.048. So the critical value is equal to 2.048. Our t value is equal to 8.09. 8.09, and that's where we leave it at this point. All right, and then the last thing is we make our conclusion. We make our conclusion, and remember we kind of broke that, even that has a structure. Okay, so we say A, in the first part we say that the t value of 8.09 is greater than the critical value of 2.048. Okay, and then what this shows, we say that this shows that there is a significant difference between the shell length. Again, we've stated what the test shows, but then we've got to make it relevant to the question, to the scenario that we've been given, that there is a significant difference between the shell length of population 1 and population 2. Okay, and we might even, since we know what that difference was, we might even want to say that in fact the shell length of population 1 was significantly higher than shell lengths of population 2. Okay, and at this point you might even want to, if in the question, like in this case there wasn't, but if in the question there is some factor that is affecting what there's some factor that's differently affecting population 1 and 2, you may even want to say at this point that there is an effect of such and such factor on the shell length. Okay, and finally, we put in the with the caveat of that there is only a 5% chance of the conclusion being incorrect. Okay, because remember we didn't measure every single mussel on the seashore or wherever. We didn't measure every single one on planet Earth, and so we don't really know. We are basing our conclusion on a small sample of a larger population, and so there's a chance that we are wrong, and the chance that we are wrong is 5%. Okay, so that is the t-test, guys. If you've got any questions, leave me a message. I'll be happy to follow this up if there's a kind of significant number of requests regarding any mistakes that I've made, or if there's any questions left unanswered about the t-test. Okay, so all the best, guys. The next video now will be on, I guess I'll do chi-squared next.